Alright, well welcome back everyone. In this example we have two blocks, A and B, which have mass of m and 3m respectively, and we're told the blocks are connected by a cable pulley system as shown in the diagram below. We're told a spring of stiffness 3K is attached between block A and ground, and that a second spring of stiffness K is attached between block B and ground. We're asked to let x describe the position of A, where the springs are unstretched when x equals 0, and to let the horizontal surface be smooth. We're asked to find the equation of motion for the system in terms of the coordinate x, as well as the natural frequency of free oscillations for the system. So because we're going to want to try to find the equation of motion for the system, I'm going to start, as I do most kinetics problems, by drawing a free body diagram. And since we're going to use Newton's second law here, I'm going to draw a separate free body diagram for each block. So if I start with block A, I can draw a two-sided free body diagram. And if I choose to do that, I'll have a normal force acting up. I'll have the weight of the block, mg, acting down. If x is positive to the right, I'll have a spring force opposing that of magnitude 3 times k times x. And I'll have some tension force associated with the cable. And I know that this block is capable of translating to the right with a mass times acceleration given by the form mx double dot. If I draw a free body diagram for block B, I'm going to have something that looks like this. Because there's two cable segments supporting it, I'll have 2t acting up. I will have the weight of the block acting down, which will be 3 mg. And I'll also have, if it's moving downward positive, let's suppose, an opposing spring force, which I'll call ky. Assuming, of course, that y is downward positive, which would make this 3 times m times y double dot. Where again the coordinate y in this case would be defined something like so. So now that I've done that, I can go ahead and try to do some kinetics here. And so to start, I'll go ahead and sum forces in the x direction and set that equal to mx double dot for block A. And if I do this, what am I going to get? Well, I'm going to get t minus 3 times k times x is equal to m times x double dot. I can then sum forces in the y direction, which is downwards positive on block B. That's going to equal 3m times y double dot. And if I do this here, I'm going to have 3mg minus 2t minus ky is equal to 3 times m times y double dot. Now if I look at these two equations, which I can label equation 1 and equation 2, I quickly realize that I have some additional kinematic variables here than I need. Namely, I have things in terms of x and y, and I need to reduce that. And so to get that, I'm going to go ahead and use a rope length constraint. And rope length constraint, of course, gives me a constraint on the kinematics of the system, and in this case, that'll be very useful. So what I'll do is I'll note that I need to add up the total length of the segments of the rope, of which there are 3. And so I'll note, first of all, that this horizontal segment up here will be some distance that's a constant minus the displacement x. So I'll have constant minus x, and then I'll have two segments over here, each of length y. And so I'll have plus 2y is equal to some other constant. I can clean this up a bit and write this as x minus x plus 2y is equal to some constant, which I'll just simply call c hat for the sake of naming. And this, of course, means that a change in x plus 2 times a change in y will equal 0. And I'm going to use this to plug in up above. Namely, if you would, this is going to give me that the coordinate minus x plus 2 times y is equal to 0, where I use x and y as I have up into the equations of motion right here. And in addition to that, I can take two derivatives of that. And if I take two derivatives of that, I'll also have that minus x double dot plus 2 times y double dot is equal to 0. Or, of course, simply that x double dot is equal to 2 times y double dot. And, of course, the above equation I can simplify and get simply that x is equal to 2 times y. So if I call this equation 3 and this equation 4, and note that they're also functions of the kinematic variables x and y and x double dot and y double dot, I can go ahead and start subbing those together to get one equation of motion. So in this regard, what am I going to get? Well, I can take equation 1 and I can solve for the tension here if I'd like. And if I do that, I'm going to get that the tension is equal to m times x double dot plus 3 times k times x. I can then take that tension and I can substitute it in equation 2. And so if I do that into equation 2, I'm going to have 3 mg minus 2 times t, which is going to be minus 2m x double dot, minus 6, because it's 2 times the 3, so minus 6 times k times x, minus k times y is x over 2, is going to equal 3 times m times y double dot, which is x double dot, divided by 2. I can then clean this up a little bit to get the equation of motion. Let me add another page here just in case I go over. And so if I do that, what am I going to get? Well, I can move first of all the 2 to the other side. I have 3 halves, and I can add an additional 4 halves to that. So I'll have 7 halves times m times x double dot, plus, in this case I have 6.5, so that'll be 13 halves times k times x is going to equal 3 times m times g. That'll be my equation of motion for the system. Now to find the natural frequency of the system, what I can do is I can divide through by the leading coefficient on x double dot, and if I do that, I'll end up with x double dot plus 13/7 k over m times x is going to equal 6 mg over 7 m, which of course is simply 6g over 7. I can look at the coefficient now in front of the x term and note that omega n squared has to equal 13k over 7m, which of course means that the natural frequency of this system is the square root of 13k divided by 7m. And that should give us our final answers to this problem. Best of luck as you work to replicate these results.